So my last 1.5 video, part 1, looks like I had some issues with recording, so just finishing the lesson in this video. So the last thing I had you do in that video, you were asked to evaluate evaluate the functions. You can evaluate the limits. So talking about what those limits then are going to equal in each of these. I'm not going to go really any further than that. You could take a look at those special trig identities. We could do a lot more, special trig limits rather. We could go into depth with these a lot more, but because you're going to learn other techniques to evaluate some of these tricky trig limits and other limits, we're going to kind of table that conversation. If nothing else, what you've learned is a new way to utilize the table feature in your graphing calculator, where you don't have to go with whatever it automatically does for you, and instead you can have it ask you what to type in. It's kind of a cool skill to be able to have with those graphing calculators. And so for part B, we can see our limit would be 0. Part C, we can see our limit would be 3/4. Part D, we could see our limit would be 0 again. So what are some algebraic tricks that we can use alongside of our limit properties to help us evaluate some of these tricky trig limits at that? If we look at part A, we can see, if we look closely, what appears to be a close representation of the trig limit sine theta over theta, as theta is approaching 0, but it's not quite there, right? We want our thetas to match. And so algebraically, if I multiply by 5 over 5, we're going to get 15 sine of 5 theta over 10 theta. Okay? Well, still, we don't have our theta terms that are matching. But if I rewrite 10 theta more cleverly as 2 times 5 theta, there I can see it. So then, using our limit properties, if I look at this, this really says 15 halves times the quotient of sine 5 theta over 5 theta. So I can use the product rule to say, well, I can break these two limits into rather than being a limit of a product, being the product of two limits. Okay, the second one is my special trig limit. That's going to equal 1. And the limit of a constant, 15 halves, is just 15 halves. So the limit originally would be 15 halves. Okay. So what else can we do with more tricky expressions involving trig functions? Take a look at part B. And look really carefully. You can see that there are 2 instances where we can see the special trig limits. The 1 minus cosine theta over theta, as well as the sine theta over theta. This quantity, we use partial fractions. We can take each of the numerators and divide by the denominator. Okay. Well, if I group 2 of these together, and instead write that as 1 minus cosine theta all over theta, right? Of course, I still have my limits with these. And then I'm adding sine 3 theta over theta. I can see the split of those two trig limits. So with my limit properties, the limit of a sum is the same as the sum of 2 limits. And I see my cosine trig limit in the first one, and not quite yet, but very closely, I see my sine trig limit on the second. Okay, on the second one, I need my thetas to match. We'll do what we did in example A, multiply by 3 over 3, so I can get my 3 thetas to match. That constant of 3 really can be thrown in front of the limit. Again, that's because of our limit properties. And so using my special trig limits, the limit of 1 minus cosine theta over theta is 0. And our constant of 3 that was being multiplied, I could bring that in front of the limit. And now the limit of sine 3 theta over theta is theta approaches 0. There we go. Is 1. 0 plus 3 times 1 is 3. So a couple different examples where you could utilize some algebra and your limit properties, as well as those special trig limits to evaluate a trickier limit. So we'll end this lesson with just another quick look at the squeeze theorem, how we can apply it with some of our transcendental functions. Okay. So number 10, evaluate using the squeeze theorem. So first thing I want you to take a look at with this limit, the limit as x approaches 0 of our function x squared times sine 1 over x. What a lot of us would want to try to do right away is use the product limit law. So that's where we would separate and say the limit of a product is the same as the product of two limits. This one specifically would be the limit as x approaches 0 of x squared times the limit as x approaches 0 of sine of 1 over x. Well, why can't we use this? Okay, we use direct substitution. This limit should be 0. But if we use direct substitution on this one, we're going to get 1 over 0. And we've actually talked about this one before. It doesn't exist. We can't evaluate it because the sine of 1 over x is an oscillating function. That's what this black function is here. That's why this graphic was provided, right? So we've got x squared, we've got negative x squared. You might be wondering, why do we have that? That'll come to play in just a second. But then this black one is what sine of 1 over x is. It oscillates, so we can't evaluate the behavior of it as x approaches 0. It's not possible. It's one of those instances we discussed in a previous section here not long ago where limits fail to exist. So then how do we evaluate this? Well, we're going to use a squeeze theorem. So to start it off, we need to start with an inequality, right? That squeeze theorem, we need to have 3 functions where one function is sort of squeezed or targeted in between the other 2. Okay? Well, if we're talking about a sine function, sine of 1 over x, what better function to use than sine? Okay, so consider, and this should say range. The domain of the sine function is not negative 1 to 1, it's infinite. The domain of the sine function, remember the sine function, there's my coordinate plane, waves back and forth like this. Okay? So the domain would be infinity, but the range, think height of the waves, or how tall the waves are, positive 1 and negative 1. Okay, so consider the range of the sine function. The sine function exists between negative 1 and 1 on the y-axis. Okay, so we then can conclude that the sine of 1 over x has to exist between there as well. Okay, about our transformations. So if we use that, we're going to multiply through by that other function. We're trying to develop this function here. So if I take my sine of 1 over x and multiply by that other function x squared, just algebraically, we're going to get negative x squared is less than or equal to, x squared times the sine of 1 over x, which is less than or equal to x squared. So now we can use the squeeze theorem, because again, this is the graphic then we're looking at up here. We've got our negative x squared, we've got our sine of 1/2. Why do I keep saying 1/2? We have the sine of 1 over x in black, and we have our positive x squared above. Okay, that sine of 1 over x is being squeezed between the other two. So remember how to use our squeeze theorem. If we can prove that the limits of these two functions as x approaches that target value of 0 is the same on the ends, from negative x squared and x squared, then we know x squared times sine of 1x, the limit of that as x approaches 0 must also be the same. So let's take a look. The limit as x approaches 0 of negative x squared would be 0. The limit as x approaches 0 of our other function, the top function, x squared, using direct substitution, would also be 0. So since the limit as x approaches 0 of both of these functions, negative x squared and positive x squared, are equivalent, and they equal 0, then we know by the squeeze theorem that limit of that function that was squeezed between them, x squared times the sine of 1 over x, as x approaches 0, must also be 0. So there's the end of section 1.5. Thanks for watching.